Hey guys, so today is April 18th and I'm going to do another LeetCode Daily Challenge. Um, so let's start. Okay, cool. Today's problem, what is it? It's a medium. Count the number of fair pairs. We've been doing a lot of like pair type problems. So hopefully I can do this one, but at the same time, wait, is this is today's problem? Oh, I already solved this, but I guess I'll just do it again. Okay, so no excuse for me to not be able to solve this is what this means. Let's go ahead and um, read the problem. So we're given a zero index integer array nums of size n and two integers lower and upper. Return the number of fair pairs. A pair ij is fair if 0 less than equal to I less than j less than n. So basically what this always means, like this kind of trips me up, but it's very simple. It's just these indices ij are somewhere in the array, right? So if our array is like this many elements, we're going to have to pick I and j somewhere inside of this range. And not only that, I just needs to come before j. And I guess that's kind of obvious, right? Because like alphabetically, I comes before j. So if this was I, then j needs to be anywhere here, right? Pretty easy to understand. But that's what that constraint means. Um, okay, the next condition is lower less than equal to nums at I. So nums at I could be like x, and then nums at j can be y. And then we just need to make sure that they are in between some bounds. And for this problem, they actually give us those bounds, right? Um, sorry, I'm trying to like fit everything on one page. But yeah, they give us these bounds, lower, upper, and they give us the array. And what is our thing? Our job is just to return the number of fair pairs. So maybe I can do like a fair count is 0. We're going to obviously process this fair count, and then we just need to return the number of fair pairs at the end. Okay, so how would I do this? I think I think just following like an example would go a long way. So like if we took example 1 and it was 0, 1, 7, 4, 4, 5, and then we'll just remember lower is 3, upper is 6. Well, what I like to do with these problems is kind of maybe whenever you want pairs, it's like um sorry, I'm kind of jumping, but it's like a linear approach, or maybe a little bit more than linear, but we're working with one element at a time. Even though pairs have to do with two elements, if we process one element and then have some like way to store it, maybe like in a hash map or something, then in the future, right, if we keep processing these elements, we will get to an element, and then we'll ask ourselves, hey, does this have a pair that we could pair it with somewhere back here in the history? And that would be in a hash map, so lookup time would be very fast, right? So that's how you could optimize these things so that we avoid like an n squared solution. And I think that's what we should be doing. But yeah, let's keep going. So lower is 3 and then upper is 6. Um, so the first one, I guess we don't really care about it because it will have no history so far. But But I guess we could have like a hash map that will store this zero. So this would be like the value. And then maybe we could store the frequency, like how many times we saw a zero. That might be helpful. So far it's the value zero with a frequency of one. Okay, whatever. Now we move on to the next element. And when we move on to this next element, what do we want? So if we're adding nums I plus nums j, let's just pretend that this was nums j. We always treat it as like the second part. So now nums I is something in the past, right? And what could nums I be in order for our like sum to be in between this? It would have to be 3 minus 1, right? At least 3 minus 1. And then it would have to be um 6 minus 1, which is 5. So we're looking for a range between 2 to 5, and we can't find anything like that. So I think that's what we're going to do. And actually now thinking of it more, we're going to scratch this pair stuff. I think we can just, I mean, I've done this one pretty recently. We can just use like a binary search. Everything that we've seen in the past, we just need to make sure that we add it into a sorted list. So like 1, 7, it would be like a 7 would process it, right? But once we get to the 4 and we add the 4, we're no longer going to have 0, 1, 7. Instead, we're going to have 1, 0, 4, and then 7. Just so that we could do like a binary search to find our lower limit and upper limit. And once we find that, then we know that this many pairs can be added to our current nums at j. So, sorry, that might not make a lot of sense, but we want to do some sort of binary search slash like a sorted list. I guess naming is kind of hard. Like, what would we name something that we've... Maybe our SL could be our sorted list. I think that's how you initialize sorted list. I haven't used sorted list. Whatever. I'll just say that this is it. And if it's wrong, we'll fix it later. So there's our sorted list. And then now we just traversed from left to right for n in nums. The lower, like lower want, right? And then we have an upper want. And these change depending on what value we are at. And that value is n. So if we were currently on 1 and we have this gap, we have this strict range of 3 to 6, our lower want isn't 3 because we already have a 1. In order to get to the 3, we just need a 2, right? We need 3 minus 1. So 3, which is our lower, minus 1, which is our n. And then same with this, it would be 6 minus 1, which is just our upper minus n. We could do... how many pairs? It would be look into our sorted list of finding... Because there could be many duplicates, right? Like let's just say we wanted to find 1. There could be many 1s. And then let's just say our lower want was 1 and our upper want was 2. We want it to give us all of these, right? Starting from the first of the lower to the last of the upper. And with Python, we could easily do this by using bisect left and bisect right. Let's just do lower index is going to be bisect left of this sorted list. and we're trying to find the lower one, right? Lower one. And then we can have our upper index is just bisect right of SL upper one. And the reason why I do bisect left is because if we wanted a 2 and we did bisect, so the reason why we want bisect right is because if we wanted a 2 and we did bisect left, it would return this index, which isn't what we want, right? We want bisect right, which if there's any repeats, it will actually return us the last one. So now that we have this, uh, 0, 1, 2, 3, 4, 5, 6, 7. It's gonna return 7. We could do 7 minus 0. 1, 2, 3, 4, 5, 6, 7, 8. So I think fair count plus equal to the upper index minus lower index plus 1. I might be off by 1, not sure. And then after this, we cannot forget to add our current n to the sorted list. So sl.add n. And then I think that's it. Let's go ahead and run that. Maybe not plus 1. We'll see, right? Yeah, not plus 1. Off by 1 is kind of tough. Why is it not plus 1? Oh, I think the reason why it's not plus 1 is because bisect right will actually give us an index of 8, not 7. I believe that's the reason why. And 8 minus 0 already gives us these 8. So we don't have to do that like plus 1 to account for the size. It's already like given. That's like the beauty of how it works, but you have to realize that at the same time. But anyways, I think that's the whole problem, right? So let me go ahead and submit this. Awesome. Wow, I guess it's super slow. It's super slow. Wait, also, did I? Okay, cool. That was today's problem. um, let's analyze the time complexity. Okay, something that runs n for all the nums. That's definitely O of n. So linear to start out with. But then we're going to have these bisect left, bisect right, which is just log n time. Adding to log n. So I think this is like so this is like log n, right? Oh, sorry. This is 1 log n. This is another log n. And I think adding is also log n. So that's like 3 times log n. So it's n times 3 log n, which is just n log n time. And then for space, we're keeping track of this sorted list. So it's going to be O of n space, linear space. Let's see the editorial. What? Yeah, they do binary search as well. And I mean, it's the same, n log n time. Yeah, whatever. Oh, maybe there's a faster way with 2 pointers. Whatever, I don't care. But that's today's video. I did it recently. Hope you guys enjoyed, and thanks for watching.